Okay, so here's our first attempt at an optimization problem. A farmer has 200 feet of fencing and wants to fence in a rectangular area adjacent to an existing fence, meaning he'll only need to fence on 3 sides, so the 4th side will be the existing fence. What is the area of the largest region he can fence off, and what are its dimensions? So, going through and thinking about some of the things we talked about, the first thing we want to understand is what we're trying to actually do here. There are a couple of things that are asked for. We want to know basically the area of the largest region that he can fence off and the dimensions of that same area. So we're going to have to sort of pick one or the other first and go for that. We'll do this by converting to an equation, and before we do the equation, I think it's going to be helpful to draw a picture. So I'm going to draw a few possible pictures so we can kind of get a sense of what's going on here. So in one case, here is maybe his existing fence, and here's the fence that he adds in. So he makes a shape that looks something like this. In this case, let's say that this dimension along this side is 180 feet. And that means that this is 10 feet on this side, this is 10 feet on this side, and there's his total 200 feet. If we look at this region, it has dimensions of 10 by 180 feet. So the area, in this case, is going to be our length times our width. That's our area of a rectangle, where in this case, we can call the length, or maybe we'd call it the height and the width, doesn't matter which we're calling which, but I'm going to say that that's 180 times our 10. Both of those have units of feet, so this has units of feet, this has units of feet, and when we multiply them we get 1800 feet squared, so square feet. So that's one possibility. If we look at another possibility, here's the existing fence again, and maybe the new dimensions are, it's much deeper this way, goes across and back down, and we have something that's in the ballpark of maybe 80 feet here. If we've used up 80 feet, that leaves us with 120 feet out, because there were 200 feet total. So if there's 120 feet left for the 2 remaining sides and we split it evenly to keep it a rectangle, that would mean we've got 60 feet over here and 60 feet over here. Doing the same thing, our area is going to be 60 feet times 80 feet for a grand total of 4,800 square feet. So obviously a much bigger area in this case. So these are the types of situations we're looking at, and we can see that clearly certain dimensions are going to give much larger areas than other sets of dimensions will give. So our goal is to find sort of the best case scenario. So at this point, let's see if we can set up some equations. We just said that the area of this thing is length times width, and we are interested in maximizing the area. So we want to, let's start with that, we want to maximize the area. And the area is equal to length times width, where for our generic drawing we're calling, here's our picture, I will call this the length and this the width. So this is the idea. But if you'll recall, one of the goals of setting this up is to write it in terms of only one variable. So right now, area is a function depends on two variables, right? It depends on both L and W. So we only want one. We want only one variable. So we're going to need to find a relationship between those two variables. But if we look at our picture, this can offer us some suggestions. We have an additional piece of information that we haven't used, right? There's a constraint. So right now, here is the equation of the thing that we want to optimize. But we have a second equation, a constraint. And that constraint is that there's only 200 total feet. So here's what we want to optimize. But we want to optimize it subject to a constraint. If there wasn't a constraint, just make the length and the width, as big as you want, and you can get as large of an area as you want. But we have a constraint. We can't just do that. So our constraint is going to give us the equation that we need to write this in terms of one variable. So our constraint is that the total length, which, looking at the way that we've got this set up, our total length is going to be the length here, this dimension along the top, plus 2 of what we're calling W. So this is sort of our perimeter. And that needs to be 200. And this gives me a second equation that I can use to replace one of the variables into the first equation. So we have a constraint on this perimeter. In this case, let's make life easy and let's just solve for what the L is here. So in this case, L is going to be equal to, I'll just subtract 2W from both sides. We'll get 200 minus 2W. And so now I can go back up to here and replace the L in the original equation with this 200 minus W, and our area can be written now in terms of only a single variable, W, instead of both L and W. So putting these together, we're combining, in this case, the equation of what we wanted to optimize, which is the area, with our constraint. And we know that the area is now going to be equal to the length, which we just found is 200 minus 2W, times the width, times our W. And we wind up in this case with an equation that looks like this. 200 W distributing through minus 2W squared. And this is, again, this is what we want to now optimize. We want to maximize this thing. So how do we find the the maximum of this thing? This now has turned into a problem exactly like what we were doing in previous sections. We're going to look for the critical points of this thing. So we are going to, in this case, take the derivative and set it equal to 0. So that's our next step here. So we are maximizing A. And to maximize A, we take that derivative. So dA dW. Taking that derivative, we will get 200 for the derivative of the first portion, 200W. And for the derivative of this piece, again, it's easy, it's just power rule, so minus 4W. And there's our equation. So we need to now set this equal to 0 and solve for what W is. So if we set this equal to 0, we will have 200 minus 4W equals 0, which will give us Moving things to opposite sides, 200 equals 4w, adding 4w to both sides, dividing both sides by 4, we get that w is equal to, let's see here, 50. And remember that this has units of feet. So w is 50 feet. So we found one of the two dimensions, but we still haven't actually maximized a yet. We found the appropriate w that will maximize a, but to actually find that maximum area, we'll have to plug it back into the area formula to figure out what a is. The other thing we're going to need to do is check and make sure that this w is actually a maximum and not a minimum. But that's easy to do in this particular case, so what I'm saying is we need to verify that w equals 50 gives a max and not a minimum. And there's a number of ways to do that. We can use our first or second derivative test, or we can recognize the shape of the function that we were maximizing to begin with. Here's our function a equals 200w minus w squared. This is a quadratic. So the graph of this thing is a parabola, and because the sign sitting in front of the quadratic term, the w squared term, is negative, we know that this thing is an upside down parabola. So this graph looks something like this. And the only possibility on this thing is that if we found a critical value, a point where the slope is 0, it must be a maximum because of the shape of this thing. But we can verify it another way as well. So we could do our second derivative test, for example. So let's just do that here for practice. Let's find the second derivative. So there's our second derivative, d squared a dw squared, and that's going to be the derivative of that piece there. And we just get -4. Because it's negative, that tells me that this thing is going to be concave down. That means that we've got a shape like this, and again, the point that we just found is a max. So we did indeed find the w, the value of w, that will yield a max rather than a minimum. So we should feel comfortable with that idea now. So let's go back, figure out the remaining dimensions. So if we go back up to the framing of the question, way back up here, there were two things that were wanted: the area of that largest region, as well as the dimensions. Well, we found one of the dimensions. We found w, so let's go back and figure out what L needs to be. And once we have that, let's figure out, let me undo that. Let me start scrolling with this over here. Okay. So we need two things. We want the dimensions, and we want the actual area. So let's find both of these. For the dimensions, we know that w equals 50 feet. That's the work that we've already done. And if w equals 50 feet, we know that L is equal to, according to our constraint equation up here, right here, that is underlined right here, or better yet, this one where we've already solved for L, L is equal to 200 minus 2w. So L is equal to 200 minus 2w, but that w is now going to be 50 feet, so equals 200 minus 2 times our 50 feet. 2 times 50 is going to be 100. 200 minus that 100 yields 100 feet. So what we've got is that w is equal to 50 feet and L is equal to 100 feet. Using that, we can find the area. The area, which again is L times w, is just going to be the 50 feet that we just found. Let me do it in the correct order. L was 100 feet, again, units of feet, times the width, which is 50 feet, for a total of 5,000 square feet. And so here are the dimensions for our final answer, and here is the area. In fact, let me sneak in the area right there. There's the area for our final answer.